Good afternoon, everyone. So, today again we are back into our lecture series on advanced hydraulics. So, today we are into the fifth lecture of the series. We are in the first module of the course. Last class we discussed on velocity distribution, and pressure distribution. In the open channels. In the end of the last class, we had given you two quiz questions, which we did not solve them subsequently, which I did not give you the solutions at that instant. Today, now I will give you the solutions of those two quiz questions. So, the first question we asked you was to determine the kinetic energy factor and momentum correction factor for a triangular cross sectional channel. Whose velocity at any point was given as half k into y to the power of half, where y is the depth from the top of the surface. So, how do you solve this particular problem? I hope most of you have done that, but still for your benefit we will just briefly solve them, how to find these factors. You know that here you need to assume that the sides of the rectangular channel, they are sloping at a ratio 1:m. The slope of the rectangular sides of the triangular channel, the slopes are 1:m. How will you find the area and subsequently the average velocity, subsequently alpha, beta? These are the things we need to find. One can easily find top width T in this case. Top width T in this case will be equal to, yes, twice m y naught. Area A, this will be equal to half into 2 m y naught into y naught. This is equal to m y naught square. Average velocity, this was given as 1 by a integral v dA. This you can write it as 1 by m y naught squared integral half k y to the power of half into dA. What is dA? Here you take any small section, small elementary section of dy height, and let the top width be b. In this case, the width of that elemental strip be b. So, you know in this case b will be equal to, if this elemental strip is at a depth y from the top, this will be equal to 2m y naught minus y. Therefore, your dA can be given as b dy or 2m y naught minus y into dy. Substitute that term here, 2m y naught minus y dy. This integral is between the limit 0 to y naught. So, what will you get here? Your average velocity v bar will be equal to k by y naught squared integral 0 to y naught into y to the power of half minus dy, or you just substitute the things, integrate and substitute the things. The final form only I will be writing here. It will be 4 by 15 into k times y 0 to the power of half. We had found for a rectangular cross sectional channel also a similar term, something related to y naught raised to half. Here also we are getting a similar way. Alpha is equal to, you know that it is v cube dA by v cube into A. It is average velocity, half k y to the power of half whole cube dA 2 m y naught minus y dy. What is v bar? So, 4 by 15 k y naught to the power of half whole cube into m y naught square. So, now you can easily guess from these things, many quantities k cube in the numerator and denominator, they get cancelled. Similarly, m in the numerator and denominator, they get cancelled off. You will get an expression, say 15 by 4 whole cube into 1 by 4 y naught 7 raised to 7 by 2 integral 0 to y naught y 0 y 3 by 2 minus dy. This you can easily find it as this alpha value, you can easily find it as around 1.5067. So, please note that this was a theoretical question for a triangular cross sectional channel, where you found the kinetic energy correction factor as 1.506. In the actual field cells and all, it is quite difficult to get this much high magnitude of kinetic energy correction factor. So, please note this may be due to because we had assumed V is equal to half into k to the power of k into y to the power of half. Maybe something wrong in this assumption or something error prone in this assumption might have led to for such a high energy correction, kinetic energy correction factor. However, we have solved it according to the principles that were mentioned. You can now compute the momentum correction factor. Beta. This is given as v squared dA by v squared A. Substitute all the terms appropriately, 0 to y naught half k to the power half whole squared 2m y naught minus y dy by your average velocity 4 by 15 k y naught to the power of half whole squared into m y naught squared. You simplify appropriately, finally you will get the momentum correction factor as 1.1718. Okay. So, this is the solution for the first question of your last day's quiz. The second question asked to you was, you were asked to find, say, for a steep rectangular channel, for a steep rectangular channel, that is having angle with the horizontal as 30 degrees, you were requested to find at a particular cross section the pressure at the bed, and at this cross section the depth of water was 0.70. You were given average velocity v bar is equal to 3 meter per second. You are now requested to find pressure P. If you recall the pressure formulation, this was given as rho g into y cos squared theta. So, this can be suggested as, say, rho is equal to, you are using the SI units, 1000 kilogram per meter cube for water, g is equal to 9.81 meter per second squared, theta is equal to 30 degrees given to you. Substitute the terms, you will get a magnitude of 5150.2 Newton per meter square. So, I hope most of you have done it correctly, this particular question. So, we were discussing in the last class on equation of continuity. So, we will continue with the same topic today. In the last class, we had derived the continuity equation, we have defined the continuity, the conservation of mass definition was given to you. Then subsequently, we had derived the continuity equation for steady flow in open channels. Say for a for two sections 1 and 2. In the equation of continuity, according to the equation of continuity in steady state conditions, we had suggested that this will be equal to in flow, the amount of or the mass of water coming into the section will be equal to the amount of water that is going out of this section. Subsequently, we had suggested the terms discharge. So, this is Q1 is equal to Q2, or if you are using average velocity term, and if this is area A1, this is area A2, it was also suggested that A1 V1 bar will be equal to A2 V2 bar in the steady state condition. So, today we will just derive the equation of continuity for unsteady state condition. In unsteady state how will your continuity equation look like? So, we will again redefine, means we will again give the same definition. In the last class we had suggested that the same definition was given to you, if you can recall them, that the conservation of mass principle suggests that the amount of water or mass of water that is coming into section 1 and the amount of water that is going out from section 2, both of them will be deferred by a value that is equal to the rate of change of storage of water between these two sections. This was given in the last class, if you recall them. So, the same thing we are again applying, or I can just again restate that the amount of water that is leaving out from section 2, this will be equal to the amount of water that is coming in from the section 1 and the rate and the change or the rate of change of water stored between these two sections. So, between these two sections the amount of water stored is here. So, what is the rate of change of stored water in between those two sections? That will give you the difference between discharges in section 1 and section 2. We will again use the same equation, that is the amount of water or the mass of water that is coming out from section 2 in a channel. You can give it as rho V2 dA2. This is equal to rho V1 dA1 plus the rate of change of stored water between the two sections. So, I can write it like this: density into volume will give you the mass of water between these two sections. So, the volume enclosed between sections 1 and 2, that is what is implied by here. So, the rate of the change in the mass of water, as this is an incompressible fluid equation, as we are dealing with incompressible fluid flow in open channels, you can easily write this as V2 dA2 is equal to V1 dA1 plus d by dt of rho dV. For our benefit, we can write, say, the total volume of water. Please note the rho term has to be cancelled off here. The total volume of water between these two sections 1 and 2, let is defined as S, as the mass of water or the volume of water stored between sections 1 and 2. So, you can write this as integral ds by dt. Proceed in the same manner as was done for the steady state condition. you know that V2 dA2, this integral term, V1 dA1, this integral term, you can approximate using the average velocity terms here. So, I can write this as A2 into V2 bar is equal to A1 into V1 bar plus ds by dt. Subsequently, you know that this is the quantity discharge, Q2 is equal to Q1 plus ds by dt, or the more familiar expression is change in storage ds by dt is equal to Q2 minus Q1. So, that is the change in storage between two sections 1 and 2 is nothing but equal to the change in discharge between the two sections. That is how for an incompressible fluid flow in an open channel can be described. You can again redefine these things. Let us assume the distance between two sections 1 and 2 as delta x, okay, or del x, delta x. If you define in this form, you can now easily suggest that the quantity Q2 minus Q1 is delta Q, that is the change in the discharge between two sections 1 and 2. Like this you can define that now, because we have suggested the distance between them as delta x. So, we can define Q2 minus Q1 is also equal to delta Q. Subsequently, you can now identify that if discharge changes in a unsteady flow open channel, in an unsteady open channel flow, if discharge changes as it proceeds from one section to another section, you can easily suggest a quantity, say dou q by dou x, that is the change in discharge per unit length. This is nothing but the change in discharge per unit length in the direction of flow. If you can define this quantity, now you can easily suggest that for between sections 1 and section 2, this delta q, I can write it as delta q is nothing but dou q by dou x into delta x, because your distance between those two sections is delta x, and this is the change in discharge per unit length. This term, if you are familiar, we can just incorporate them here. Now, consider any cross section of the channel. You know that the top width is T. This in the unsteady flow, in the unsteady incompressible flow, the variation in discharge can be now easily identified by how the depth of the flow, say the depth of the flow y, and how the top width, how both the quantities changes with respect to time, that can be easily correlated. In the same section, it will vary with respect to time in unsteady state conditions. Those property you can now incorporate here. Let us take an elemental strip from the top width. Let us take this elemental strip. this is of dy depth. So, you can define a quantity dA is equal to T into dy. So, whatever change in storage and all are occurring, that can now we can now easily correlate with the change in the top width as well as change in the depth of flow. We will come into that here, or you can suggest that your top width is dou A by dou Y, that is change in area, change in the area by change in the depth. Like that also you can now define T is equal to dou A by dou Y from subsequently from this relationship. This is just for our analysis. Once you define it in this form, now you can suggest that the rate of change of storage, rate of change of storage we had given this as ds by dt. How can you identify it through the thing here? Between this strip of length delta x, the volume is getting changed or the stored water is getting changed. If A1 is the area here, A2 is the area here. Now, let us suggest that any amount of water changing or this area cross sectional area into del x, that will give you an approximate volume or the stored water in this section. So, let us come into that. The rate of discharge, now I can just give this as d by dt of area of cross section into del x. We are just suggesting this in this following form. If you recall the top width and the area dA, the change in this dA now can be correlated here. You can subsequently bring it that quantity here. I can suggest now ds by dt is nothing but d by dt of the change in area dA at each time, that is change in area dA into del x. So, the same phenomenon, you know, this is T dy del x, or you can write it this as d by dt of dou A by dou y into dy del x. This can be approximated now. We are suggesting, because we have just taken an arbitrary length delta x, which is not varying with time. That is delta x, it is for our convenience we have taken some length. You can, this can be approximated now subsequently as delta x dou A by dou y into dou y by dou t, that is the change in depth of flow. Your storage is now become a function of change in depth of the flow. So, ds by dt is now approximated as delta x dou A by dou y into dou y by dou t. So, continue the formulations. You got ds by dt is equal to del x dou A by dou y into dou y by dou t. You also have seen that delta q, this can be given as dou q by dou x into delta x. So, in the section, therefore, I just rub that in the channel stretch for section 1 section 2 in this channel stretch, we have suggested, say, if Q2 is the discharge from this portion, Q1 discharge entering here, ds by dt the change in storage between the two sections. If in our analysis, if we are taking the outflow from the section as positive, and if we want delta q as positive, if we want delta q as positive, that means Q2 greater than Q1. That implies, if Q2 is greater than Q1, that naturally implies that the amount of water stored between the two sections 1 and 2, it is getting reduced. So, the amount, the volume of water, if it is getting reduced, that is definitely a negative quantity. So, we will suggest now here delta q or dou q by dou x into delta x, this is equal to minus of delta x dou a by dou y by dou t. I hope you understood that why I took the negative sign here, because volume, this quantity is for the volume, increase in volume is positive and decrease in volume is negative. If you want, if you decide that the outflow or the outflow from section 2, discharge from section 2 as a positive quantity, or if you want delta q as positive, then accordingly the volume of water stored, it will get reduced. Therefore, I am writing it the negative sign here. You can easily form the equation here, cancel off the repeating quantities, dou q by dou x e plus dou a by dou y into dou y by dou t. This is equal to 0. Or in a more famous way, I can write the unsteady flow continuity equation as dou q by dou x plus t into dou y by dou t is equal to 0, where t is also function of y. So, this is the famous continuity equation in unsteady fluid flow. So, our next topic is on energy equation. Till now we discussed on the equations of continuity. Next is energy equation. So, energy, the term energy and all, you are quite familiar with those quantities and all. Even in your elementary hydraulics or even in your school physics and all, you have studied various energy terms, kinetic energy, potential energy and all. You have even studied the terms how energy can be represented as energy head. Most of you should be aware of that. The energy can be easily represented as energy head. So, what do you mean by representing energy as energy head? Let us take a channel stretch of inclined slope. Let us suggest this as the water surface. Now, there are two sections here. section 1 section 2. Please note that I have drawn the section based on considering the depth of flow and not the normal distance from the water surface to the bed. That is not the case given here. You can define streamlines for fluid flow in the open channels. If I take, say, at any streamline of fluid flow occurring there and any point, say O, if you consider any point O, this can be now suggested, say, if it has a normal distance dO from the free surface. From the free surface, if you draw a normal distance to the bed and if this point is at a distance d naught, if this streamline is at a distance d naught from the free surface. Naturally, we have done the other quantities and all, you know that this can be given as y naught and all. We will come into those discussion. Let us consider a datum line, and this point is at an elevation ZO from the datum line. If this is at a ZO, the slope of the channel, it is theta with the horizontal plane. Your energy head or total energy head, this can be now given as summation of pressure head plus velocity head plus datum head. Okay. So, one can easily give the total energy head in terms of pressure head, velocity head and datum head. These things most of you have studied even in your school days and all. How do you account the things here? How you want to represent now energy equation for open channels and all? What does the things here suggest? What is pressure head now? For this particular case, say for this at this point in the streamline, at this point in the streamline, what is the pressure head? Pressure is P0, pressure at O, at point O, it is P0, your pressure, this you can give it as, say, rho g d0 cos theta, right? Or even you have studied like this, rho g y0 cos squared theta, if this is y0, that also you have studied, right? So, let us what is the pressure head quantity? Pressure divided by rho g. So, you will get the quantity d0 cos theta. Your datum head, this is equal to Z0, that is from your datum line, how much elevation is there for that particular point in the streamline. Your velocity head, This is given as the velocity at this streamline, at this point in the streamline, V O squared by 2g. So, your total energy head H at the point O in the streamline, this can be given as d0 cos theta plus V, it is not 0, it is O, do cos theta V O squared by 2g plus Z O, right. Similarly, you can define energy head, for different streamlines in the fluid flow in open channels. You can define them. If you take any cross section now, just take any cross section, maybe section 1 or section 2, there also now you can define energy head. There also you can define energy head. Say if this is Z1, this is Z2, then subsequently you know that this is Y1, this is Y2, right. H1, that is the energy head for the channel section 1. This can be given as Y1 cos squared theta plus Z1 plus, here you need to incorporate average velocity term, and once you incorporate the average velocity at this section 1, you need to provide the kinetic energy correction factor here. So, therefore, I have to multiply this energy equation in the velocity head, you have to multiply the term alpha. Similarly, at section 2, you can easily obtain this thing y2 cos squared theta plus z2 plus, if this is alpha 1, let this be alpha 2 v2 squared by 2g, or if you are suggesting in terms of d, if this is d1, if this is d2 depth, your h1 will be d1 cos theta plus z1 plus alpha 1 v1 squared by 2g, h2 is equal to d2 cos theta plus z2 plus alpha 2 v2 squared by 2g. So, please note that when you are taking the whole channel cross section, not a particular point in the streamline and all, when you are taking the whole channel cross section, there you are taking the average velocity term and subsequently you have incorporated the correction factors. So, what does the energy equation suggest? Just now I have given the expression only for the total energy head term. So, what does the energy equation suggest, or energy conservation of energy suggest? Conservation of energy or the principles of energy, what does that suggest? It suggests that the energy, total energy at any section 1 and the total energy at any section 2, they will be deferred only by a quantity where the energy loss is occurring, or you can suggest that the total energy head at 1 is equal to the summation of the total energy head at section 2 plus the loss of energy that has occurred between sections 1 and section 2. So, that can be given there as H1 is equal to H2 plus some loss in energy, loss in head or loss in energy. So, energy you are expressing in terms of head here. I hope most of you have understood that term head has units of length. This has units of length. Even though this is an energy equation, the dimensions are in terms of length. So, here some units of head loss is occurring there between two flow. When the flow occurs from one section of the channel to the other section, there will be some head loss. You need to account that also, and the conservation of energy suggests H1 is equal to H2 plus whatever loss in energy has been there. So, you can now easily write these thing terms as H1 is equal to, again I am just reinstating that, H2 plus HL. Various head losses are head loss due to friction and head loss due to eddy formations. So, in most of the, you can give this as HF and this as HE. In most of the prismatic channels, this quantity is avoided. Eddy formations are almost negligible. So, HL in most of the cases is approximately same as your loss due to friction. So, that quantity if you suggest it, you will see that H1 is equal to H2 plus HL. You can express them in the expanded form which were given that earlier. This is either you can write it in terms of say y1 cos squared theta plus z1 plus alpha 1 v1 squared by 2g. This is equal to y2 cos squared theta plus z2 plus HF, because we are considering that the channels are mostly prismatic here. Once you write the equation in this form, this is called the energy equation in a more expanded form. When you write it in the energy head form, this is an energy equation, or if you write this particular quantity in terms of the depth, normal depth from the surface to the bed, d1, that will be d1 cos theta plus z1 plus alpha 1 v1 squared by 2g is equal to d2 cos squared theta plus z2 plus or most of the open channel flows, your theta is negligible. In most of the cases, theta is negligible. This equation then subsequently becomes z1 plus y1 alpha 1 v1 squared by 2g. This is equal to y2 plus z2 plus alpha 2 v2 squared by 2g plus HF. So, in most of our open channel flows, we can use this particular energy equations. in most of the cases. Exception means, however, for higher slope channels, please note that you need to account the appropriate cos theta values. Otherwise, you can use this particular relationship. You will see that this equation, suppose if your energy correction factor, if it is 1, if head loss due to friction, if it is 0, and what does that suggest? Suppose in such cases, you will find that Z1 plus Y1 plus V1 squared by 2G is equal to Y2 plus Z2 plus V2 squared by 2G, that is, this is equal to a constant, and this is your famous Bernoulli's equation that is applied in your fluid flow problems and all. So, Bernoulli's equation is also a energy equation. So, now we will come into the quiz for the following today's lecture. Let me ask you, say if there is a rectangular channel, if there is a rectangular channel, the depth of flow is y, width of the channel is b, there is an unsteady flow in this particular rectangular channel, unsteady fluid flow in this particular rectangular channel. Find the partial differential expression for equation of continuity in this rectangular channel. Find the partial differential expression for equation of continuity in this rectangular channel. A hint is that discharge through a cross section, this is equal to, discharge is equal to area of cross section into average velocity. I am just giving this particular hint. Now, you derive the, or you have already derived the unsteady flow equation of continuity. Using that, just get an expression, partial differential expression for the equation of continuity for rectangular channel. Hardly it will take 30 seconds, I hope so, and it is quite easy. And you just tell me what type of equation it is, how, means how many dependent variables are there and how many independent variables are there. In a partial differential equation, what is meant by dependent variable, what is meant by independent variable. These things are clear, I hope so, for you people, because this is a master's program, or you should need to refer your undergraduate books again. What is meant by dependent variable in a partial differential equation, what is meant by independent variable in a partial differential equation. Your second question for the quiz. Your second question is, for any fluid flow, from section 1,1 to section 2,2 in a channel, for any fluid flow in the channel from section 1,1 to section 2,2, what happens to the total energy term, whether it increases or decreases. Give reason. Say you have just computed what is meant by total energy. So, from section 1 to section 2 when the fluid flow occurs, whether the total energy term increases or decreases, you just tell me. Fine. The Q solutions. For the first question, you know the unsteady flow equation, dou q by dou x into, yes, tell me, dou q by dou x plus t into dou y by dou t is equal to 0. Q is equal to A V bar, T is equal to same as your B, A is equal to B y. Substitute the terms here, you will get your partial differential equation in the following form: B V bar dou y by dou x plus B dou y by dou t is equal to 0, or V bar dou y by dou x or you can say dou y by dou t is equal to minus V bar dou y by dou x. So, you just suggest me as an assignment what type of partial differential equation is this one. The solution for question number 2 is that energy will always decrease from one section to another flow in the direction of flow. In the direction of flow, energy will decrease. There is no point in gaining energy if there is no external source of supplying energy and all. So, that way we are concluding today's lecture. So, in the next lecture we will be starting the specific energy terms and all. Thank you.